Hello, everyone. Welcome to this talk about the rolling shortwaves asset in 2XKO's Scuttler Strand. My name is Mathieu Dufresne. I've been working as a tech artist at Riot Games for 6 years now, where I helped to ship Legend of Runeterra, and I spent a little bit over 4 years on 2XKO. Before that, I was in Ubisoft for 15 years, where I was lucky enough to cross the paths of people like Benoit Martinez, Kim Goossens, and Vincent Fortin, who have all contributed in their own way to ignite a flame in me about procedural generation and moving vertices procedurally. And in fact, this flame about shader maths, especially Vertex shaders and procedural generation, is what I would call my tech art love language, if you'd allow me. While coding doesn't really come quite as naturally to me as it does for many in the tech art circles. Vector maths, on the other hand, has always felt surprisingly intuitive to me since I first got introduced to them a couple of years ago. So perhaps some others in here feel the same way, and if that's the case, I have great news for you. There's exactly 0 line of code in this presentation. And despite me not doing much code, I'm sometimes able to spin up some fun things like this little guy here that we internally call the eel lantern, and that you might recognize from the Brazen Hydra stage in 2XKO. So this is another example of motion that I created using nothing but the Vertex shader. So there is no skeleton, no rigs involved. All of it is just points being moved around through the Vertex shader. And for today, we're going to be looking into this specific Vertex shader, the rolling waves of Scuttler's Strand stage in 2XKO. While the whole shader is a little bit too big to go over entirely, I tried to break it down into easy to reproduce components that, when combined, should get you on your way to reproducing this effect on your home. So that's one of the major takeaways that I hope for today. And if I do this presentation well today, I hope that another one of your takeaways is going to be that there is actually very little rocket science involved in the making of this asset. The complexity arises from stacking a lot of fairly simple concepts layered on top of each other. Now, there is certainly complex maths under the hood in terms of rendering, engineering, to produce this kind of asset, but the Vertex shader itself remains hopefully quite digestible. With that said, now, I also won't lie, despite the concepts being relatively simple, the presentation is pretty dense, and there will certainly be a fair amount of mental gymnastics involved, especially towards the end of the presentation. We will be looking at a lot of shader graphs. There will be a lot of bright colors, and there is really just a lot to say in these 45 minutes, so let's get on our way. Here's an overview of what we'll be covering today. First, we'll be looking at some of the concept arts and prototypes from the very beginning, as well as a bird's eye view of the whole shader. Then we'll explore a concept that I call the linear wave, which I consider to basically be the backbone of the shader. Then we will talk about making ourselves some data visualization tools to help us understand and debug our shader. And last but not least, we will talk about phase shaping, which would be the actual sculpting of the wave shape. So without further ado, let's look at these concepts and prototypes. So these are the original beautiful concept pieces from Kyle Whitaker under the supervision of Anthony Xenakis, who is the stage's team lead on 2XKO. At this point, we didn't really know how far we would be able to push this asset. A lot of you probably know that water as a key asset can be often quite difficult to manage. So we needed to do a bit of R&D to see where and how far we could push this idea of having this front and center in our stage. So based on these images, we set out to explore an idea that I had of blending cross sections. And here is a slightly more refined plan for this idea that I had, which in a nutshell is about making shapes that are morphing through time and blending in space. So I know this whole shapes morphing through time and blending in space thing sounds a little bit like a quote from Neil deGrasse Tyson in a sci-fi documentary. But this is actually what we're going to be doing, so bear with me, and hopefully, as the presentation moves forward, this will make more sense to everyone. What we're trying to build here is a shader in which each vertex is going to understand which of these cross sections, or phases as I call them, it is part of, and based on this, how it should offset itself as the wave is passing through it. So here is the earliest prototype video that I could find where I was testing a simplified version of this whole concept that I explained. This one had maybe 4 quickly made cross sections and was fairly basic, all things considered, but it was enough to convince my manager, Jeremy Ernst, to let me continue the research in that direction. And here's a slightly more advanced version of the prototype where the shapes are more nicely defined and where we're starting to get a good sense of the rhythm of the shader. At this point, I think we could say that we had achieved the confidence required to commit to this technique as our main direction for this asset. So we went all in on this one. Okay, so now we'll have a look at a bird's eye view of the shader. It's probably a bit overwhelming, so I'm just giving a little bit of a warning here, but here we go. So this is the whole shader. There's probably not much that you can actually see here, but one thing that you can notice is that I am using a lot of named reroutes so that I can keep things compartmentalized in boxes and avoid having long dangling wires all over the place. It helps me to keep things nicely grouped together in terms of features in the shader. So if we break it down into the various sections, the top part here in yellow would be the pixel shader, which unfortunately we won't have time to cover today, as we'll mostly be focusing on the vertex shader, which I believe is the most intricate part of this shader. Then in green, this tiny little block here is what I call the custom time, where I simply implemented a few parameters that provide me with very precise control of the flow of time in the shader. I wanted to talk a little bit about it, but for the sake of time, I decided to skip this section in this presentation. But really, it's just about giving me precise time control to help me debug my shader. Right below it in blue is what I call the linear wave section, which is one of our main topics today. Towards the center in purple, we have the main shader input-output section, which we won't really be covering in depth today because it is simply where the main shader node is and where I collect input data to drive other parameters in the shader. So we will be glancing at it here and there during the presentation, but there is really nothing too special about it. And now, top left corner in red here, we have our debug visualizers section, which is going to play a super important role in our workflow. Then in green is the final vertex shader output section, where I assemble the phases and add some more layers of world position offsets to beautify the motion a bit using noises and such. For the sake of time, we'll only be looking at the phases assembly part today. And last but certainly not least is the phases shaping section. So all these faces that we assemble in the previous section, we have to build them somewhere, and so this is what we are doing here. This is where we are basically sculpting all of our cross sections. So now that we have a rough idea of what's coming our way, let's go ahead and have a look at what the linear wave and how it is built. So this is what we see here. So the linear wave is the main driving force of this whole shader. In its simplest form, it's really just a repeating linear gradient from 0 to 1, which we obtain through our mesh's UVs, and it is scrolling along the surface of our mesh, scrolling on the surface of our mesh. Once this part is achieved, we simply mask out some of those gradients to break the pattern a little bit, and that's it. Everything else is built on top of this. So I know to some people in here, this might be a very simple thing to do, but because it is so foundational to the rest of the system, we'll have a look at how to build this thing. So the first step on the left, what you see here is the mesh's UVs as we would see them if we were to output the UVs in the emissive color of the shader. So UVs are 2D vectors. So when used as a color, they occupy the red and green channel, respectively, U and V. And if we isolate just the U component, we end up with this perfect black and white linear gradient from 0 to 1, which spans the width of our mesh. Now, if we multiply this U component by a value greater than 1, much like when we're tiling textures, we will be tiling our gradient pattern. However, the numerical values being output by the multiply node here will no longer be from 0 to 1. For example, if we multiply it by 5, they will be from 0 to 5. But we do want to make sure that our data remains between 0 and 1 because we want to drive a system with these values from 0 to 1. So this is where the Frac node becomes handy. Frac will return only the fractional portion of your scalar, of the scalar that you feed it. So 2.3 would return 0.3, 4.75 would return 0.75, etc. Once we have this pattern, we can now add the notion of time in the shader by simply adding a time node in between our multiply and Frac nodes. And this is what gets our pattern to crawl at a fixed speed over the surface of our mesh. In the next step, we will want to skew our pattern along the length of the mesh. So to do this, we will be adding the V component of the UVs on top of the U component that we already extracted. So the V component is also a gradient from 0 to 1. But unlike the U component, which stretches along the width of our mesh, the V component stretches along the length of our mesh. And so multiplying this V component by either a negative or positive value before adding it on top of the U component, as we see in the graph, will effectively skew our pattern on one side or the other, respectively. And the final step that we'll do today, as far as the linear wave is concerned, is going to use a modulo and saturate operators to mask out some of our waves. The combination of modulo, saturation, and Frac that we see here might be somewhat more exotic to some people, so we'll have a very quick look at what it does, just to make sure everyone is tagging along, and we will try to achieve the effect that we see in the picture here. And I also promise that this will be the highest level of maths that we will be doing today. Before we move on, just notice that the operand, the second operator of the modulo fmod node here is a value of 3. We will be using that in a second. So we'll quickly hop in Desmos here. The way to visualize this is just like a function. The horizontal x-axis is the value that we send to our function. The y-axis is the value that comes out after being processed by our function. So what we see here in blue is the regular linear progression of the unmodified value of x, or in this case, the R channel in the top right image. Meaning that if you follow this graph, a value of 2 in x will return a value of 2 in y. This is just the input data coming into our function, and we're not modifying it. Now, if we take this x value and we feed it into a modulo by 3, just like in our node network 2 slides ago, this is what we would get. Modulo by 3 means that as the value of x increases, we will continue to be looping through the values between 0 and the operand, 3 in this case. So as we can see here in the graph, 1 would return 1, 2 would return 2, but as we hit an x value of 3, the modulo function would loop back to 0, such that 3 would return 0, 4.5 would return 1.5, 5.7 would return 2.7, and then once we reach 6, the value returns to 0 once again, and so on forever, creating a pattern that loops from 0 to 3 to infinity. Then we want to add the saturate operator, which simply clamps our values between 0 and 1, flattening our curve when they used to return between 1 and 3. So this is what we see in green here. So we now have a pattern that goes from 0 to 1, stays at the value of 1 for a while, and then loops back to 0 and start over again to infinity. And lastly, it was getting a bit crowded in the graph, so I cleaned it up a bit, but here we are connecting everything that we just did to our Frac operator, which causes the flat line that was previously at 1.0 to go down to 0, since the Frac operator keeps only the fractional part, and the fractional part of 1.0 is 0. So instead of having a flat line at 1, we now have a flat line at 0. So now our final pattern goes from 0 to 1 linearly, then immediately resets to 0, and stays there for a while, and then once again goes from 0 to 1 linearly, and so on. And so putting all of this together is how we go from the pattern on the left that we started with to the pattern on the right, which gives us spaced out linear waves. And here, for all intents and purposes, the linear wave is done. The only thing that is missing would be the noise pass on top of it, which we will not be deep diving into it in this particular presentation. There's many, many ways that you could do this. In my case, I've just decided to stack a bunch of sine waves at different amplitudes and frequencies. And as you can see in this video, in fact, if we remove the wave masking and add a few more waves and crank up the wave distortion all the way, you can literally see these sine waves crawling through my mesh. But for the sake of time, I will leave it to your imagination to figure out how you want to do this noise, as it is largely a matter of preferences. Okay, so the linear wave, one of the backbones of our effect, is now done. Now, I want to talk about data visualization, but before that, we have to talk about a little tool that I made, which I called a multi-vector Lerp. And that is a core component of this shader. So hopefully, understanding how it works will help us understand better how we are going to use the linear wave as the main driving force of our shader. So let's get to it, multi-vector Lerp. On the left here is a regular Lerp node using color inputs, and on the right is another much bigger node that is somewhat intimidating right next to the main material node. That would be the multi-vector Lerp that I was talking about. And so first, let's look at how a regular Lerp deals with color on the left. If you have input A, which is red, and input B, which is green, and the Lerp alpha parameter is going to smoothly interpolate the RGB values from color A to color B as it goes from 0 to 1. The multi-vector Lerp function does exactly the same thing, but it does it multiple times over. So it has 10 inputs for vectors, which in this case are colors, but could also be positions. And it also has that same Lerp alpha parameter that drives the whole thing. So just like the regular Lerp, it will smoothly interpolate the RGB values of your color from one input to the other, and to the other, and to the other, all the way until its value is 1, and it reached the 10th input color. One thing I like about working in Unreal is that it comes with a whole lot of pre-made material functions that can actually be looked into and learned from. They're usually those blue ones that you see here. So that multi-vector Lerp thing is not something that I invented or whatever. I just knew of the existing Lerp 3-color node that comes with Unreal. And as I was designing the system, I just thought, this is exactly what I need, but I just need to be able to scroll through much more than 3 colors or 4 colors, because the version with 4 colors also comes with Unreal. And so I barely just opened up the Lerp 3-color node, had a look at how it works, which is what we see on the left here. And replicated the functionality in my own custom material function so that instead of lerping through 3 colors, we'd lerp through 10. So this is what we see on the right side. And so by inspiring myself from some of these out-of-the-box material functions nodes, I actually came up with one of the key components of this wave asset. You'll see we're going to reuse it all over the place. Over the years, I've personally learned a lot just from looking into these nodes. There's a ton of them, ranging from very simple to very complex. So if you're interested in shaders but haven't yet developed this habit, I strongly recommend that you start peeking in those. Okay, so moving on. Now that we understand how that multi-vector lerp node works, we can finally look at how it is used in our debug visualizers. I've made 2 main debug visualizers. We'll understand as we go, like how they function and how their purposes. Just ride along with me for now. The first one is called the single wave debug color, and the second one is called the phases debug color. So it's probably hard to see now, but both of them are using the multi-vector lerp, and both of them are using the same color scheme as input on the left side. The only difference is that they use a different input connected into their lerp alpha parameter. Let's look at what the phases debug visualizer does first. So in a nutshell, the purpose of the phases gradient is to show which phase of the wave should each section of my water mesh be displayed. I am generating this colorful gradient simply by using the U channel of the UVs on my mesh as the lerp alpha parameter of my multi-vector lerp. So what we see here is what it would look like if I had left the original UVs unprocessed or perfectly linear and pass it as the lerp alpha value. So as you can see, there is a perfectly even space between each phase. In reality, though, we want to be in control of the length of those phases, as you know, the phases of the life of a wave don't necessarily evolve at an equal pace, all of them. So I am modulating the U coordinates using a curve atlas as seen here. So as an example, we can see here that the buildup of the wave is quite slow. But then when we reach about 0.6 in the U values, which is roughly 60% of the distance towards the beach, this is where we want the wave to kind of fold on itself and crash. And so the speed at which we evolve through each phase dramatically increases, just as an example. And so after this modulation, this is what my phases debug color looks like, or what you would call my phases gradient looks like. And so this, again, represents which of these cross-sections, of the 10 cross-sections that I have, we want to be displaying as the wave moves along the mesh. So here, just to help with the clarity, I'm superimposing the linear wave on top of the phases debug color, and hopefully this helps understand the idea here. What we want to do with this gradient is identify which one of my 10 phases or cross-sections should be sculpted as the linear wave is moving across the phases. We'll get back to the sculpting of the phases itself in a bit, but before that, let's move over to the second debug visualizer that I made, which is called the single wave debug visualizer. As we've seen before, the single wave debug visualizer uses the same color pattern as the phases debug visualizer, but instead of using the mesh's UV's U parameter as input for the lerp alpha, it is using the linear wave that we just saw 2 slides ago and that we built a couple of minutes ago. So while the phases debug visualizer is a static data set in the sense that it does not intend to change at runtime, the single wave debug visualizer does have motion to it because the linear wave has motion. And this is what it looks like when we visualize it gliding through our mesh. So what we were looking at in the previous slide is a visual representation of where my virtual control points, these points that you see along this graph that I had made, I call them virtual control points. And it's a visualization of where they should be. And I kept the same color scheme, so hopefully that helps. These are the control points that we will use to sculpt our wave cross sections. And each phase will in turn to be able to determine which of these profiles I should be using along the mesh. So the job of the phases visualizer is to inform on which phase each vertex is located on. And the job of the single wave visualizer is to inform about where the wave currently is and which control point should currently be affecting each vertex. What we see here on the left is a compositing of the single wave debug colors patched on top of the phases debug color. Now that we know where each phase is located, and we also know where each of the virtual control points are at a given time as they are following the linear wave, if we add a 2D offset at the location of each of those control points, we can create an actual shape based on what phase we are on and which control point of the linear wave is currently impacting the underlying vertices. Okay, so now we have our theory and we have great visualizers to check out our shader. That's awesome, but we've done a lot of stuff, and now just before we move on to the phase shaping section, I just want to make it very clear that the colorful visualizers that we just looked at, well, they really are just that. They're visualizers, and they actually don't have anything to do in the final shader. So it's not like colors driving weird magical things in my shader. It's really just to help me visualize what is going on my shader. And personally, I find that, being able to visualize my stuff helps me understand my data, and it is often key to success when working on more complex shaders. The theory that you have in your head and what is actually happening in your shader is very often two different things, so being able to visualize it is very important to me. Especially when troubleshooting issues, I find it very useful to have reliable way to know that my shader foundations are still good, and having this kind of visualizers pre-set up in my shader, as opposed to building them on the fly when I would happen to need them, it always helps me to iterate faster, and it mostly helps me to keep my focus where it should be. So again, to wrap up this section, the visualizers and the colors themselves are not actually doing anything. The values that are actually important and that will be driving our shader, the same way that they have been used to drive our visualizers just now, are the linear wave and the modulated U coordinates of the mesh UVs. Both of them will be driving their own set of data through the multi-vector Lerps alpha parameter. And these two together is basically the foundation of the effect. Okay, again, we have our theory, we have our foundation. Let's talk about the actual shaping of the waves. So as the shader run, each vertex looks at these two sets of data, the linear wave and the modulated U coordinates, and basically uses it as a lookup table. So say our very good friend vertex 3756 is being processed. It will know that it is part of, say, phase 6, because that's what the modulated U coordinates will tell it. And then it will look at the linear wave data, and this will give it the information it needs to know two things. First thing is the wave currently on top of me? And if the value returned by the linear wave is 0, it means that no, the wave is not on top of you. And if yes, if the value is higher than 0, then great, but which control point of the wave should I be following? So say control point number 4 in this case. Yeah, so how do we do this in real life? So the sculpting of the cross-section part is that very tall section of the shader graph overview, the one on the left. This is where phase shapes, the phase shapes that we've seen a couple of times and that we see here again are being generated. So let's have a look at closer look at just one of them. So here we are zoomed in on the sculpting of phase 5. All other phases would look exactly the same as this one, with the exception of phase 1, phase 2, and phase 10, just because they are either just flat, because it's the beginning and the end, or because they are significantly much simpler in terms of sculpting, so I could process them in a more efficient way. But all the other, actually sculpted shapes look exactly the same as this. First and foremost, there is this obvious, gigantic, and once again, probably fairly intimidating node here called the make wave shape. We'll be looking at it in just a minute, but first, let's look at our environment here and what we have around it. So, firstly, here in red, we simply have a bunch of named reroutes, which are bringing in data that has already been processed elsewhere in our shader and are being brought back here to help with the sculpting. So we have the number of waves. We have the height of the waves so that we can control the height of all the cross sections with just one parameter instead of adjusting them all individually. We have our now famous linear wave, and last but not least, we have a simple vector pointing in the direction where the wave will be folding onto itself. So it's just a constant direction that I defined in the shader input-output section. In Unreal Lingo, you could call this that it's the wave's forward vector. Then in pink up here, these are simply two scalars representing the horizontal and vertical offsets of control point number 4 when it is in phase 5, because we are looking at phase 5 right now. And as you can see, each of the 10 control points have their own horizontal and vertical offset, except once again for point 1 and 10, because they are flat, because it's the beginning and the end. And yeah, so we're keeping them flat to keep them at the same level as the underlying mesh, so no offset for them. And so for all of these horizontal and vertical offsets, they're all being fed into that big make wave shape node in yellow right here, along with the other pre-computed data. It might be difficult to see, but this make wave shape data simply has 4 inputs for those 4 parameters in red here. And then it has 1 input for every single horizontal and vertical offset per point. So it looks very big, but that's all there is. So let's have a quick look at what's happening inside this make wave shape node. This is where we will be assembling all of our horizontal and vertical offset together as vectors so that they can collectively become kind of a field of world position offsets that will be driven by our linear wave and scroll across our mesh. We'll just be zooming in on the highlighted green part, which, as you can see, gets repeated multiple times for each virtual control point. So here on the right, in the red box, and feeding into the material functions output, is our good old friend, the multi-vector Lerp, once again. And its Lerp alpha value is driven by the linear wave that we have received as one of our parameters. And what it is receiving for the vector inputs is for each control point, a vector that is being built in 2 steps. The first step can be seen here in yellow. We take our vertical offset scalar, which is simply being multiplied by our wave height, and it gets used as the z component of our vector. And then here in green, the horizontal offset scalar, slightly more complicated, but not that much, which is first divided by the number of waves on our mesh, because of course this would affect the size of our wave. If there's more waves, your vector needs to be smaller. And then this gets multiplied by the wave folding direction to make sure that our offset goes in the direction where we want it to go. And yeah, so basically so that it happens in the same direction as the wave is traveling. And so adding these 2 pieces together gives us a vector that represents the offset that we want to apply through this particular control point. And now we can use that input for our multi-vector Lerp as an offset. So now that we have all of this hooked up, I know this is all a lot of theory, let's look at how it works in real life. So remember that what we are doing here, we're simply giving horizontal and vertical offsets to our virtual control points from their initial flat position to achieve a given shape. So in this particular phase, point number 3 would have a horizontal offset of, say, minus 300, and a vertical offset of maybe 7. Again, the horizontal offset numbers tend to be bigger because they have to be divided by the number of waves. So this is why we're talking about minus 307, but ultimately they're just a number in space. And here, just as another example, point number 9 would have a horizontal offset of maybe plus 50, and a vertical offset just a little bit higher than point 3 at maybe 8 or 9, all right? And so going back out of our make wave shape node, let's assume that we are working on a brand new phase where all the offsets are set to 0. I will connect the output of this phase directly into the shader's world position offset, and we will have a look at what this looks like in action. And so here we see the phase is connected to the world position offset. Then here is our properly wired make wave shape node. And then you can see that all our values are zeroed out. So if we were to give a vertical offset of 25 to our yellow control point and apply the changes, you can see that only precisely where the yellow control point can be seen, we now have a vertical offset as the wave moves forward. The denting effect is just an artifact of interpolating somewhat extreme shaped values here in this demo, so please don't bother about it too much. And then we can add a horizontal offset of 500 and a yellow on the yellow control point, and we can see that it is now leaning towards the beach. And so this is how we slowly sculpt our wave for this particular phase. And then if we go to our green control point, we can give it a vertical offset of minus 25, which will effectively send it below the rest of the control points. And as you can see, it is right now underwater, under the ground. And so we have achieved shape control over our mesh as the linear wave is moving across the mesh. Likewise, if we take the output of a fully sculpted cross-section and send it directly to the world position offset, we will be getting that particular cross-section being sustained all across the mesh as the linear wave passes through without evolving into a different shape. And this is what we are looking at here. So it's a single cross-section. It does not evolve. It is just moving across our mesh and deforming it as it goes. And so after diligently doing this methodically for every single control point on every single phase, you end up with your complete wave life cycle, as we've seen previously. Okay, so now we've output each of our phases into one of those named reroutes, as we see here. And we finally reached the point where we want to cycle our 10 phases. So this is what we're going to do next, and this is also going to be the last step that we cover in depth together today. So as we've just seen in the last video, outputting a single phase directly in the world position offset would give us a constant deformation of that particular phase scrolling through the mesh. So what we want to do is basically that, but with the added functionality of cycling phases 1 to 10 sequentially. And so what tool do we have in our arsenal that was built specifically for that kind of purpose? Well, if you thought about our newest, bestest friend, the multi-vector Lerp material function, you are correct. So we just need to hook up all of our phases as inputs and phase 1 and 10 receiving, respectively, no offset, and a tiny vertical offset of -1 for the 10th phase, just to make sure that it stays underground as the wave reaches the beach. And to drive the multi-vector Lerp alpha input, we're using the very same modulated U coordinates that we have used earlier as we were creating our phases debug visualizer. So the same way that our linear wave is now driving the control point offset, our modulated U values will now be controlling which of our phases is being displayed, or which of the phases cross-section we should be using for our control points. And this is what we would get if we were to connect the output of that multi-vector Lerp node straight into the world position offset of the shader. So what we see here is for each vertex, the phase now determines which cross-section to use. The linear wave is defining which specific control point to use, and each control point drives the offset of the underlying vertices. And with that, we're done with the foundation of our vertex shader. At this point, the only thing left to do as far as the vertex shader is concerned is to add some more layers of noise here and there. I also added some upward displacement using the foam texture, which had the, frankly, very unexpected but very interesting side effect of creating these nice little tendrils that we see where the water meets the shore. Totally unplanned, it just kind of emerged out of the shader by itself, but it looks great. So, and speaking of the shore, I want to do a quick shout out here to my colleague Niels de Wit, who made the system that allowed us to blend the color to the shore wave with the color of the shore itself, so that we can have a smoother and more eye-pleasing transition, as can be seen here. All right, so we're basically done. So here's just a few takeaways from my experience of building this asset to wrap up the session. The first one would be keep noise for the end. Noise is often the icing on the cake that helps make things pretty, but noise is still noise. Yes, it can and probably will make things pretty, but it certainly does create noise in your capacity to read, visualize, and validate your data. And it's not just in visual terms. Your code or your shader graph will get bloated and by adding noise as well, as we can see here. And yeah, everything is just going to be much more difficult to read and get a sense of. So just like with icing on a cake, try to keep noise for the end and try to compartmentalize it as much as possible. Ideally, if you can turn it on or off, that's always useful. And then I know this gets said a lot, but let me say it once more. Working clean was definitely super important in this case. I think we all know that in real life productions, there's very little time actually allocated to tidying up and making sure that everything will be understandable to your future colleagues. And it's not just for your future colleagues, it's even for yourself. At some point, things can become larger than we anticipated. And if you haven't kept your playground tidy, well, you might not even be able to track back the work that you did yourself. So work clean from the start and keep in mind that there is no such a thing as over-commenting. Or maybe there is actually, but until it becomes an actual problem for you and that your colleagues, like reprimand you for over-commenting, I think you can safely assume that you are not over-commenting. About the importance of the debug visualizers in the development cycle, I cannot emphasize enough how these became the main development tool of this asset. From quite early on, I realized that my data set was very difficult to visualize in my head, especially when interpolating across multiple data sets. The results can sometimes be surprisingly unexpected. So the debug visualizers were not an idea that I had. They kind of naturally surfaced by themselves as I was trying to work on this and understand what is happening with my wave. But the real winning step was when I decided to organize them and parameterize them so that they are easily accessible for me to toggle them on and off at will very easily. And last but not least, the power of using ranges from 0 to 1. If you have to remember a single thing from this presentation, I would suggest that this might be it. It's certainly not a revolutionary idea. It's also certainly not something that I invented, but working on this asset made me notice even more than I already knew how powerful the range from 0 to 1 is in mathematics in general. If we think back at the main driving force of our wave, it all comes down to a gradient from 0 to 1 sliding on top of another gradient from 0 to 1. that's literally it. That's what drives the whole thing. There are a lot of math operators that always output a range from 0 to 1, like Frac, saturate, smooth step, uh, even to an extent dot product, sine and cosine with a bit of processing. And then there's also another group of math operators that become intricately useful or powerful when they are used specifically within a range of 0 to 1, like the power, step, or 1 minus nodes or operators. I think for some of you, what I'm saying now, it might be very common or simple knowledge, but hopefully this presentation might have lit a spark for some of the people in here. And if you did get intrigued, I strongly recommend that you start looking into this 0 to 1 range thing, or what is sometimes called a normalized range, and start trying to understand all the things that you can achieve with it and learn how to wield it as a tool. I've personally been like toying with it and learning about it for well over 10 years. And to this day, the more I use it, the more new interesting things I discover about it. So there. And that wraps up the presentation. I hope you enjoyed. Thank you very much.